All right, for section 3.6, we're talking about the chain rule. And the chain rule comes into play when you have a function inside of another function, when we're trying to find the derivative of composite functions. So composite just means you've got a function inside of another function. So here we want to first identify what function is on the inside. So that's this guy up here. We're going to call that u. So u equals 4x minus 3. Which then if I'm doing a substitution here and I replace the 4x minus 3 with u, then my y equals e to the u. Now when we do the chain rule, we're going to find the derivative of the pieces and multiply them together. So it's derivative of the outside times the derivative of the inside. So the derivative of e to the u is e to the u, and we're going to talk about that one in a couple of sections, but that's the nicest derivative on the planet. And then the derivative of 4x minus 3 is 4. So right now we've got y prime equals e to the u times 4. The problem is I want this derivative in terms of x. So once you get these derivatives, you then substitute back in for your u. So our y prime would be e, we'll put the 4 out front, 4e to the 4x minus 3. And that's our derivative. Now, sometimes they do the chain rule on questions you don't need to use the chain rule for. I will totally agree with you on that one. This one we could straight up just do the derivative. You should recognize that this is a power rule. So we would get 36x cubed, and then bring this one down, so 12x. So that's our derivative. However, they're asking us to use this concept of compositive functions. So they've rewritten it as this polynomial quantity squared. These are equivalent. So here, anything in that parenthesis, that's our inside function. That's our u, 3x squared plus 1. Which means I'm left with u squared for my outside function. So the derivative of my outside function is 2u, and the derivative of my inside function is 6x. And you should recognize right away that makes no sense to have u's and x's. We want one variable. So we get y prime, I'm going to multiply 2 times 6 is 12. There's my x, and then the u was 3x squared plus 1. I just kind of put them all together. Now you'll see if you were to actually distribute this, you end up getting 36x cubed plus 12x. And gosh, it's the same thing that we got right up there. So either way will get you the right answer. So the chain rule, as you've been seeing, we're doing the derivative of that inside function times the derivative of the outside function. So we've got f being a differentiable function and g being a differentiable function. So if g is on the inside of f, then the notation would look like this. We're doing the derivative of the inside function times the derivative of the outside function at g of x. So I want you to make sure you've got that notation down. That's going to help you, especially on those problems with tables. You're going to have to write these out in symbols and then plug the numbers in. Now Leibniz, he's another mathematician. Him and Newton, this is Newton's notation. So Leibniz and Newton always got into battles as to who was more calculus-y and who was more correct. Neither of them is more correct than the other. They both were the founders of calculus. But Leibniz is the guy who came up with the dy dx notation. And so in his notation, this actually makes a lot of sense. Dy dx, that's derivative of y with respect to x. If you look up here, we did a derivative of u with respect to x. So we're going to write that down. Derivative of u with respect to x. And we multiplied that by the derivative of y with respect to u. derivative of y with respect to u. So when you multiply these, math magic occurs, and the du's cancel out, and look what you're left with, dy dx. It's amazing. So whichever notation you prefer, it does not matter. They both get you to the same end result. So on example 3, it says we've got an object moving along the x-axis, so the position when time is greater than 0, that's an important detail, is given by cosine of t squared plus 1. They want to know the velocity of the function of t, as a function of t. So what we should recognize is we've got an inside function and then an outside function. So my inside function was t squared plus 1. And my outside function is what's left now, and it's cosine of u. So I'm going to use Leibniz notation here. I'm doing the derivative of x with respect to t. Now I'm going to change this because I want to use the same notation they are. They used x here. X equals. Kind of obnoxious, but they do that a lot. So here we're looking for dx dt, derivative of x with respect to t. So with Leibniz notation, he says, all right, do the derivative of u with respect to t times the derivative of x with respect to u. Those u's are going to cancel out. So what is the derivative of u with respect to t? Well, this is just 2t. And then the derivative of x with respect to u, derivative of cosine of u is negative sine of u. And as we know from earlier, I can't leave it with t's and u's. They want this with respect to t, so I have to plug my u back in, which was t squared plus 1. So if I combine all of this, we get negative 2t sine of t squared plus 1. That is the derivative. So I want you to try example 4. Similar type of a question, you guys try that one. So I recognized my inside function was x squared plus x. My outside function was then sine of u. So if I'm going to do those two derivatives, derivative of the inside was 2x plus 1. Derivative of the outside was cosine of u. So when I put them all together and I replace that u, we get 2x plus 1, parentheses, cosine of x squared plus x. Good work.